We are going to apply Euler's method to this initial value problem. So the ordinary differential equation we have is dy dt equals 1/2 times y. Our initial condition is y at t equals 0 equals 1, and we're going to be using a step size of delta t is equal to 1. All right, so the first thing, let's see, we're going to identify our f. So f of t comma y is equal to, it's just 1/2 y, it's not dependent on t. Our t sub 0, well, that's that number right there, so it's equal to 0. And our y sub 0, well, that's this number right there, so that's a 1. So let's get started. So I have t sub 0, I have t sub 1. So t sub 0 equals 0, and y sub 0 equals 1. Now I want to compute t sub 1. Well, that's equal to t sub 0 plus delta t. Okay, well, t sub 0 was 0, and delta t is 1, so 0 plus 1, so t sub 1 is 1. All right, and let's compute y sub 1. So y sub 1 is going to equal the previous y sub 0 plus delta t times f of t sub 0 comma y sub 0. All right, and if we write that out, so y sub 0 here is 1 plus delta t, that's a 1. Our f function is 1/2 y. We've plugged in y sub 0, so it's going to be 1/2 times y sub 0. Y sub 0 is 1, so we get a, times 1. If we add those together, we get 1 plus 1/2. That ends up being 3 halves. All right, so that's our t sub 1, y sub 1. Let's go ahead and do t sub 2. So t sub 2 equals t sub 1 plus delta t. Okay, well, t sub 1 was 1, and our delta t is 1. So we have 1 plus 1, so we're at 2. Then y sub 2 is going to equal, right, y sub 1 plus delta t f of t sub 1 comma y sub 1. Okay, well, y sub 1 ended up being 3 halves plus 1 times, I have f of t sub 1, y sub 1, so it ends up being, 1/2 times y sub 1. So we get 1/2 times y sub 1. Y sub 1 is 3 halves. Okay, a little more calculation there. So this is 3 halves. This ends up being 3/4. 3 halves plus 3/4 ends up being, let's find out. So 3 halves plus 3/4, well, that's the same as 6 halves, 6/4 plus 3/4. So it looks like this ends up being 9/4. All right. Let's go a few more times here. So then we're going to do t sub 3, well, that's t sub 2 plus delta t. Okay, well, that's, and I'm going to save room, that's going to be t sub 2 was 2, and then delta t is 1, so that's a 3. And really, if we do t sub n, it's going to be n, right? We're always just adding 1 to it. But here we go, y sub 3, that's y sub 2 plus delta t times f of t sub 2 comma y sub 2. Okay, well, y sub 2 was the 9/4, and plus 1 times, right, the 1/2 times y sub 2. Y sub 2 is 9/4. And I'm gonna just go ahead and say what that one is. That one ends up being 27/8 if you work it out. So if you might notice a pattern here. So if we do t sub n, well, that ends up just being n, right? So t sub 0 was 0, t sub 1 was 1, t sub 2 was 2, t sub 3 was 3, right? T sub n is going to be the number n. And this one, it might be a little harder to, see the pattern before we do a few more, but what ends up happening if we have y sub n, we started with 1 was y sub 0, y sub 1 was 3 halves, y sub 2 was 9/4, and y sub 3 was 27/8. And so actually there's a pattern to that. It ends up being 3 halves to the n. Right, so if n is 0, I get 3 halves to the 0 power. Well, a number to the 0 power is 1, and that's y sub 0. If n equals 1, then I have 3 halves to the first power. Well, that's just 3 halves. And yeah, y sub 1 is 3 halves. And y sub 2 is 3 halves squared. So 3 squared is 9, 2 squared is 4, so I get 9 fourths. There's the 9 fourths for y sub 2. And for 3, we get 3 halves to the third. 3 cubed is 27, and 2 cubed is 8. And that was the 27/8. So this is actually the pattern it follows. Most of the time you won't be able to get such a nice thing like this, but this is going to be an intuitive example here. So what that ends up looking like, and it's not going to be to scale, I'm going to try my best. So that's t, that's y, and let's say this point here is 1. So it started out, it went up, then up, then up, then up, and up, something like that. The numbers are increasing quite a lot. And so this one ended up being 3 halves. This point here ended up being 9 quarters. This point here ended up being 27/8. This point here will end up being, let's see, 381 over 16. So I don't think that's the scale. So now intuitively, it has the shape, it looks like an exponential. If we actually solve this equation here, this dy dt equals 1/2 y, the solution, y of t, I'll put it over here, y of t is equal to e to the 1/2 t, and I forgot my constant in front, so let me just squeeze that in. It's a constant times e to the 1/2 t. In our case, our constant, so y of 0 equals 1, well that equals c times e to the 0. So c is just 1 actually. So then for our initial value problem, y of t is just e to the 1/2 t. But if we write that out, so that's the same thing as e to the 1/2 all to the t power. E to the 1/2, another name for that is the square root of e. We're bringing that to the t power. The square root of e ends up being about, all right, it's an endless number, but it's about 1.6487 ... to the t there. The equation we have for y sub n is 3 halves to the n. And so 3 halves, that's 1.5. And so our n here is kind of like t, when t is an integer. And so the reason that we're going to get a nice agreement between Euler's method and the exact solution to the differential equation, this y sub t equals square root of e to the t, is 1.6487, whatever, is about 1.5. So if I actually draw out what this looks like here, this number will grow a little bit faster. So it's going to look something more like that. So that's actually square root of e to the t. So intuitively, this is a nice problem. This is why Euler's method works. You're kind of following the slope field. This one works nicely because you can actually solve this y sub n term exactly. You don't just have to keep going over and over and over again. You can calculate the nth term without calculating all the terms before it. And intuitively, this is why it works. The approximation Euler's method as this 1.5 to the n, and the real solution is approximately 1.6 to the t. And so that's the idea. So we're going to do a couple more examples after this, and if you can do this thing 3 times, you can do it 1,000 times. But you will end up needing a calculator on these next 2.